Hello students, in this session let us solve this question of shear force and bending moment diagram. We are given with a cantilever beam of 2 meter length. You can see here total length of the beam is 2 meter and it is a cantilever beam as it is fixed at one end and free at other end. And the load are given at different points, and this is point load. That is 800 Newton at D point, 500 Newton at C point and 300 Newton at B point. We have to draw the shear force and bending moment diagram for this question. So let us solve this question. As usual, we cut here, we will draw the shear force bending moment diagram and cut the section. You can see here that between D and C there is no force, so we can take one section between D and C. Between B and C there is no force, we can take one section between B and C, and B and A there is no force, we can cut one section between B and A, and we can find out the shear force for each section, and that will be valid between D to C. Another will be valid between B to C, and the next will be valid between B to A. So we have to take three sections here, right? So let us take one section here, suppose this section, and this is at a distance x. This is at a distance x from the D. We are taking from D. We are taking this section, suppose x, capital X section is there, and it is at a distance x from the D. And what is shear force? Sum of all the forces to the right or to the left of the section. Sum of all the forces to the left or to the right of the section. So we can take the sum of forces to the right of this section, and this is only one force, right? There is only one force to the right of this section, right? So what will be Fx? Fx, that will be equal to, and sign convention, you must remember the sign convention also. I can draw sign convention here, that these are the sign convention. You should remember, this is positive shear force and this is negative shear force. This is shear force. And what about bending moment? That is positive. This is this type of shear force we have taken positive, I think, right? And this is hogging bending moment, and this type of bending moment I think we have taken negative. This we have taken positive, and this we have taken negative bending moment, right? So you should remember the sign conventions, or you can take your own sign convention also, that is not a problem, but follow the same sign conventions in all the questions, right? So we have taken a section x. Well, what is the force on this section x? So sum of all the forces to the right of this section, and right of the section, this is rightward downward direction. So rightward downward direction is positive. You can see here rightward downward direction is positive. So I can take this 800 as positive, and simple 800 is there, so it remain constant. So 800 will be there. So this will remain uniform throughout this section, and this will be valid. This will be valid from D to C. Valid from D to C. It will be valid. So what will be the force at D? Force at D will be 800. And what will be the force at C? That will be again 800. Right? So it is 800 Newton positive from D to C. So you can draw now the diagram. Suppose this is the baseline. Let us take, because we have to cut more sections also, so let us take somewhat downward so that space may be there. So here we can take, so that we can utilize this section. Yes, this is okay, right? So this is point, these are the points A, B, C and D, and at D point force is 800 Newton. So 800 Newton is like this up to this point, say this is 800, and this is uniform. This is uniform from D to C, like this, right? Like this, right? So this is 800 Newton. 800 Newton, and this much force is achieved up to this point, right? So we have reached here, from here to here we have reached now, right? So this is the force between D to C. Now you will see that we know that whenever there is a force, there is abrupt change in the shear force diagram, right? So there will be abrupt change in the shear force diagram when we take the cross section here. When we take cross section here, there will be abrupt change in shear force diagram, right? So suppose this is the x now, or x1, say this is x1 and this is capital X1. So what is the force, shear force at this x1? So what is shear force at this x1? Fx1, that will be equal to all the forces, algebraic sum of all the forces to the right of the section, 800 plus 500, right? So this is 800 plus 500, so this will be 1300 Newton, and this will be valid from C to B. So at C, the force will be 1300, and FD, the force will be 1300, and points we have found out the force. So it is change, FC 800 to FC 1300. So 800 to 1300 we have achieved like this, right? And then it is constant, right? So it was 800 and there is some jump of 500, right? So this is 500. So this was 800 and this force is 500 Newton on the suitable scale. You can make a scale of that also. So this was 800 Newton and this is 500 Newton, right? So total is 1300 at C point. What it means? That there is change in force, shear force at C, and to the left of C, just left of C, there is the force is 1300 Newton, and to the just right of C, the force is 800 Newton, right? So there is abrupt change in the force of C, right? Similarly, we can take section here also. We can take one more section here like this, and this is the section taken from D, right? So this is suppose x2 and this is section is suppose capital X2, right? What is the shear force at x2? Fx2. So that will be equal to algebraic sum of all the forces to the right of the section, 800, 500, 300, 800, 500, 300. So this will be equal to 1600 Newton, and it is valid between B to A. So this is valid between B to A, right? So you can take at extreme points at B, what is the force? At B, it is this force 1600, it is constant, and FA also 1600, right? So we have already made 1300 load, 300 should be added, so add 300 here. So this will become at B point, this is 1600, so 1600. So we have added the 300 of load here, right? 300 Newton, and then 1600 load at B will remain constant till we reach at point A, and this is the 1600 Newton load at A point, right? So this is the shear force diagram, and it is positive throughout the section of the beam, throughout the length of the beam, right? So this is how shear force diagram is drawn for this question where there are three forces, right? Similarly, we can draw the bending moment diagram. How can we draw the bending moment diagram? Bending moment diagram we have to draw. So let us say this is the reference line on which we want to draw the bending moment. This is A, B, C and D, right? And we have to draw the bending moment. Say bending moment is mx at this section, mx. So what is bending moment? Mx. That will be equal to, so what is bending moment? Algebraic sum of all the forces to the right or left of the section. So let us take to the right of the section, because we are already taking the right section. So to the right of the section, this is one force 800 multiplied by perpendicular distance, that is x, 800x. So we got 800x, this much Newton meter of the movement, and this will be valid between D to C. D to C. So what will be the movement at D, at the end points? This will be 0 because x is 0 there. And what is the bending moment, because x is 0 here? You should remember that this is x is 0 here. And what is the bending moment at C? At C x is 0.8, 0.8. So put value here 0.8. So MC will be equal to 800 multiplied by 0.8, because the value of x is 0.8 here, right? So you will be getting the value. So what is the value of movement at this point? This is 640 Newton meter, right? So this is the value. This is the value at C point, 640 Newton meter, right? So we can draw the diagram now, but one thing is there. Oh, we have forgot the sign convention. This 800 Newton to the right in anti-clockwise direction, clockwise direction is negative basically. You can see here in clockwise direction, in towards right is negative. So here we should write the negative also. So we have forgot that. We should write the negative here. So MC will be equal to 800, sorry, negative again, I again forgot, negative of 800 multiplied by 0.8. So this will be equal to minus 640 Newton meter, right? Minus 640 Newton meter is the force, and this equation is a linear equation because x is there, right? So it will be a linear variation. So from 0 to 640 Newton, linear variation. 0 to 640, suppose this is 640, suppose this is 640, and there is a linear line from here to here, like this, right? So this is 640, so this point is 640, this point is 640 Newton meter, 640 Newton meter, right? So we have drawn the curve from D to C, right? Next. Now C to B, we have taken this section x1. What is the moment at this section? Algebraic sum of all the forces. Two forces are there, 500 multiplied by perpendicular distance, 800 multiplied by perpendicular distance. So 500 multiplied by 800, both are clockwise at rightward, means negative, right? So mx1 will be equal to minus 800 multiplied by x1 and minus 500 multiplied by this distance cx1. What is cx1? That is x1 minus 0.8. So this is mx1, 800 x1 and 500 multiplied by this distance cx1. This is because this is perpendicular distance of 500 from x1, right? So this is the bending moment at x1. And what are the peak points? That are C and B. It is valid between C to B. If it is valid between C to B, put the value at C. What is the value at C? MC. And what is the distance of x at MC? That is 0.8. So put here the 0.8 value. So you will get 0.8 minus 0.8 will be 0, and multiply 800 multiplied by 0.8, you will get the same value, 640 Newton meter. So this is 640 Newton meter, right? This is MC. And put value, now you should remember that whenever we are applying a load, there is no change in bending moment at that point. So you can see here, although we are applying load, but the bending moment is not changing at this point. In this section, just write the value is 640, and just left there is the values again 640, right? And what is that value at B? MB. And MB. Now MB, B is at a distance of 8.8 plus 0.7, 1.5 meter, and it means x is 1.5 meter, right? And when we are saying MB, it means what we are taking is, we are taking x as 1.5 meter, right? And what is the MB? Put the value of x here, 1.5 and 1.5, and what you get value get, calculate it, put value 1.5 here as well as 1.5 here. Why we are using 1.5? Because B is at a distance of 1.5 from D, right? So because x1 is taken from D, so that's why we are taking 1.5 here, right? So MB is at x1 is equal to 1.5. Find the value of MB. What is the value of MB? So this will come out to be 1550 Newton meter. Solve it and you will get this value. And what was MC? MC was at x1 is equal to 0.8 meter, right? So these are the two values we have obtained. Minus 1550. So 640 to 1550. 640 to 1550. Suppose this is 1550 and the variation is linear. Linear variation is there. You can see this is a linear variation. So draw a linear line from here to here like this, right? And you will get the value. And this value is, what is this value? This value is 1550 Newton meter. 1550 Newton meter, right? 1550 Newton meter. From 640 to 1550 with a linear variation. Now, next, take the section x2 between A to B, right? And from, it is at a distance x2 from D, and take the bending moment, and bending moment the algebraic sum of all the forces. So there are three forces, 300, 500 and 800. So mx2, find out mx2, you will get mx2. What is mx2? 800 multiplied by x2, 800 x2 minus 500 multiplied by x2 minus 0.8, 500 multiplied by x2 minus 0.8 minus 300 multiplied by x2 minus 1.5, x2 minus 1.5, right? And this is valid. This is valid between B to A. It is valid between B to A, right? It is valid between B to A. Now, what is the value at B and what is value A? MB M at B. When we are talking about MB, the value of x at that point is MB, value of x2 is at the point is 0.8 plus 0.7, that is 1.5. So means we are talking about 1.5 meter length. So put the value of x2 as 1.5 meter in this equation and you will get the value of mx2 or MB at x2 is equal to 1.5 meter. So what is the value of MB? So MB will come out to be same, minus 1550 Newton meter. So it will come out to be same, minus 1550 Newton meter. Check it, put the values and you will get the same value, because there will be no change when at a point where the load is applied, right? So there should not be any change in the bending moment at this point, right? So this is 1550. Next is MA at a distance x2 equal to, how much is the distance? This distance, this is 2 meter length. So entire 2 meter length. So that will be equal to, put the value of x2 at 2 meter here and you will get the value of MA. So what is the value of MA? 2350. So this is minus 2350 Newton meter. 2350. So 1550 to 2350 variation with a linear variation. This is a linear line, right? Linear variation. So suppose this is 2350 somewhere here. 2350. Make a linear line from here to here like this, and this value is 2350. Newton meter, right? And make it a straight line here, vertical line, right? So this is the diagram for our this bending moment diagram, right? So and these lines are straight lines, these lines are straight lines, right? And this is negative, this all bending moment diagram is negative, isn't it? So this is how the bending moment diagram and shear force diagram is drawn for this question.